Okay, this is our final lesson with engineering application to the spreadsheet application to engineering. So this is with the channel routing, and we specifically use the Muskingkum method of channel routing. So this is the explanation, and you have the inflow flow volume, and you have the outflow volume. So usually the flow depths height decrease at the velocity increases as you move the downstream. So you might have two different storage. This part is called the prism storage, and this one the wedge storage. And this is a way you calculate the prism storage as a linearly related with the outflow discharge. And whereas the coefficients are introduced like to form the wedge storage, generally certain percentage of this is the inflow. Okay, and the difference between the inflow and the outflow will be the to certain percentage. It will be the percentage inflow and percentage the inflow minus the outflow with a certain percent, and the x values ranges from 0.0 to 0.5. And usually for natural river system it is up to 0.3. And so how can we come up with a given the characteristics of our Muskingkum equation? So Muskingkum equation helps us to estimate the flow at certain points downstream by using this equation. For example, this one is the natural change in storage equation. You can equate this equation with the Muskingkum equation. You can finally come up with this one. So these are the coefficients C1, C2, and C3. So in order to find out the Q at time t plus 1, you have to go with C1, C2, and C3. You have to find them, and you can actually get the x value that best fits your situation by iteration. And if you find x, you can find your k. If you can find your k and x, then C1, C2 will be determined. If you have C1, C2, then you can easily determine the discharge at certain points downstream. So here is our data, the time, the inflow data and outflow data that this particular we have. So the first step is to find the inflow minus the outflow in a meter cube per second. So this is in a meter cube per second, and this is equal to the inflow minus the outflow directly. Okay? And this is what you get. Then we have to calculate the mean storage. We actually say that the change in inflow, the difference between inflow and outflow is the storage. Then mean storage, if you want to calculate the mean storage, at time t is equal to 0, we have a 0 storage. But at time t is equal to 1, we have the average of time 1 and time 2. So this is average plus this one, so divided by 2. Now if you have to get the k values in terms of days, you need to introduce the mean storage in the form of meter cube per second per day. So we have the delta t 6 hour. So if you multiply this by the ratio of the delta t 6 hour to the days, we will have this value in a meter cube per second per day. So you can calculate these values in the same principle. Okay, now you can calculate this accumulated storage, accumulated storage. Okay, in this case at this time we have 0. At this time we have the previous storage plus the current storage, current mean storage. Then make the other two be calculated by the same way. Now once you found this is your accumulated storage S, and then you have to calculate your storage in somewhere else. And the other way we can calculate the storage is by using this one. So if you use xi plus 1 minus xq to calculate the other storage, and we will be able to find our k as a slope of the relationship between the two curves. So here is another equation, which is inflow times the x value plus 1 minus the inflow, 1 minus the x in times the outflow discharge will give you the storage. And then say assume the x value. This is a natural river, and you can assume x value between 0.3 to 0.0 to 0.3. Then you can assume 0.3. So for 0.3 I can calculate this value. So this is equal to inflow times the x value, which is this one, as this constant. I should fix that, and plus 1 minus the x again, and that is constant value, and then this is multiplied by the outflow, the discharge outflow. So this is what you get, and do the same thing for the rest. This is what you find. Okay, now you have to draw the s on the x-axis and this on the y-axis, and see what you got. Insert the curve. So this is what you have. Then this is your curve. In this we have ix plus 1 minus x into q, and then this we have the s. Okay. And then the optimal value of x, this is the x, and this value depends on x. So we only find the optimal value of x when this curve is narrow enough, okay? Which means when the estimation as we go upward and downward meets each other, when they are the same, then that is our optimal x value. So you can change this x value to 0.1 to see that. So this is better than 0.3. Maybe if you decrease this one 0.05. So this is open. No, it's not good. So let's increase to 0.125. And this is getting better. Let's increase to 0.15. So this is where we can attain a better one. So if you go to 0.175, it is getting open. So 0.15 is a better one. So once you find this, feed this line with a trend line, which is linear trend line, and find the equation on chart. Okay. Then in this equation, okay, the slope of this equation will be your k value. So the inverse of the slope of this equation, which means 1 over 2.3819 will be your k value in days. Okay. So this is how you do the Muskingkum routing in Excel sheets.